Let's look at what happens when solids dissolve in water. There is a competition between the forces of attraction. So we have solvent-solvent attraction. Here we've got water molecules, and those are attracted to each other by intermolecular forces. Dispersion forces, dipole-dipole forces, and for water, hydrogen bonding. So there's a lot of interaction and attraction between the water molecules. Sodium chloride, table salt, we're trying to dissolve that in the water. There are solute attractions between the particles of the solute. For sodium chloride, that's going to be ionic bonds, also very strong attractions. In order for this solute to dissolve and mix in the solvent, we have to break apart the solute-solute attractions, and we have to break apart the solvent-solvent attractions and replace them with solvent-solute attractions. This is why these interactions and those interactions have to be similar in order for a solution to form. Water is polar. Ionic compounds are extremely polar, and so we do get significant interactions between the solvent and the solute. But that's not always the case. There are ionic compounds that do not dissolve in water. Calcium carbonate is an example. The exact why some ionic compounds don't dissolve and others do is way beyond the scope of this class. But basically, the attractions between calcium and carbonate ions win. They are too strongly attracted to each other, and they're not going to give that up to mix and mingle with the rest. Okay? Any questions about that? We've talked about solubility before. We learned how to use that list of rules to predict whether things were dissolved. And then in chapter 15, we learned how to actually calculate how much will dissolve. And now we're kind of talking about the why and how behind things dissolving. So here's a chunk of table salt, sodium chloride. When this dissolves in water, we have to separate the sodium ions from the chloride ions. They really like each other. Positive and negative charges, they're very attracted to each other. But we somehow have to tease them away from each other. Water does this by surrounding the negative ion, the chloride ion, with its positive side. This replaces that force of attraction that the chloride felt for the sodium. It takes more than one water molecule to do this, but a whole bunch of water molecules will come and surround it and make the chloride feel comfortable being away from the sodium. Water can do the same thing for the sodium ion by surrounding it with its negative side. The partial negative side of water helps to comfort, you could say, the sodium ion. So we got positive and negative charges, and this is good, right? There's an attraction here. So the sodium ion is attracted to the water, and it's lured away from the sodium chloride. There's all sorts of interesting and crazy analogies we could go into, but I will try to restrain myself. So we put sodium chloride in water, the ions separate. They will mix thoroughly and uniformly with the water, forming a solution, a homogeneous mixture. We've got individual sodium ions, individual chloride ions mixed in the water. The solubility of a compound is usually defined as the amount of the compound in grams that will dissolve in a particular amount of liquid. Often that's how many grams of this will dissolve in 100 grams of water. The solubility of sodium chloride at room temperature is 36 grams per 100 grams of water. What that means is if you have 100 grams of water, you can dissolve 36 grams of sodium chloride in it. If you had 200 grams of water, you could dissolve 72 grams of sodium chloride. If you try to put more in, it will not dissolve. That's the limit, the maximum solubility. A solution that has the maximum amount of solute is called a saturated solution. It's full. Like a sponge can be saturated with water, right? If you try to soak up more water, it won't go in because it's full. A saturated solution is full of solute. It can't hold any more. If you add more, it'll just sink to the bottom and it will not dissolve. It's full, saturated. An unsaturated solution contains less than the maximum amount. There's room for more. So if you add extra solute, it will dissolve. You can add extra solute until you form a saturated solution, and at that point, no more will dissolve. So there's saturated and unsaturated, and then we have the crazy one, the supersaturated solution. This holds more than the normal maximum of solute. That sounds contradictory, doesn't it? This holds more than the maximum. How does that work? Well, these supersaturated solutions are not stable, and not everything can form a supersaturated solution. Normally, if you disturb this in any way, the solute will precipitate out and you'll be left with a saturated solution. These can form under special circumstances. So you take a can of soda. Actually, I think I have a picture. No, I don't. Never mind. A can of soda. Soda is fizzy because it has carbon dioxide dissolved in water. The way they get the carbon dioxide to dissolve in there is they put a great deal of pressure of carbon dioxide in the can, and that forces carbon dioxide to dissolve in the water. When you release the pressure, you have a supersaturated solution, and what will happen is the bubbles will start forming, the carbon dioxide will start coming out. And you can see that happen when you open a 2-liter bottle of soda, especially one that has a clear, like maybe a 2-liter bottle of 7-Up or something in a clear bottle. You open the lid, and you hear that psh sound as the pressure escapes, and then you start to see bubbles forming. The bubbles are coming out because under the new conditions without the pressure, it's got too much carbon dioxide in it, it's supersaturated. The other way you can form a supersaturated solution is by heating the solution. What we'll learn is that if you increase the temperature of the solution, the solubility usually increases. So here's an illustration of a sodium acetate solution. You warm it up and make a saturated solution at a higher temperature, and then you let it sit there and cool down without disturbing it. What happens is it will slowly cool down. As it cools down, the solubility decreases, but the solution doesn't really seem to notice. This is like when the Roadrunner and Wile E. Coyote, somebody runs off a cliff in the cartoons. They should fall immediately, right? But they don't. They run until they notice that they're in midair, and then they fall. So a supersaturated solution is a little bit like Wile E. Coyote before he notices that there's nothing under his feet. It's suspended in midair in an impossible situation. Once you disturb it, though, in this illustration, they're taking a crystal of sodium acetate and dropping it into the supersaturated solution. Once you disturb it, you kind of wake it up, say, hey, you're supersaturated. It goes, oh no, I can't do this. And then all of that extra stuff precipitates out. And we see these crystals forming away from that crystal that was dropped in. And eventually, there's a whole lot of solid in there. And that's a supersaturated solution. I had a couple videos to show you here. These don't have sound, so don't worry, you're not missing anything. So this is supersaturated sodium chloride. Sodium acetate. And he's going to disturb it. So he sticks a rod in there, and you see those crystals forming? Isn't that neat? He just stuck a rod in there. That's all he's doing. But it was supersaturated, and by sticking the rod in there, it disturbs the solution, and the crystals began to precipitate out of solution. Because there's too much, it can't stay there, and so they all come out. And it gets basically solid with crystals. The temperature does change. It gets warm. But the rod itself was just room temperature. Just sticking a plain old rod in there. This is another one. These people are having an awful lot of fun. So those are just some toothpicks they're sticking in supersaturated sodium acetate. Looks like pom-poms. It doesn't take, and see the temperature there, 52 degrees. That's up from 25. So when this happens, there's a significant amount of heat that's given off. But she can disturb it with her finger, with a thermometer, pretty much anything. Yeah, anything that disturbs it. Sometimes when you really want it to not get disturbed, even just thinking thoughts that the solution doesn't like or looking at it wrong will cause it to precipitate. See, it's almost solid. It's all squishy and wet. Yeah?
And when they disturb it, does the solution just go back to being saturated?
Yes, it just goes back to being saturated. Here they're pouring supersaturated sodium acetate, and when it hits something and gets disturbed, it becomes a solid, and so you can make castles with it. And then she touched it, and now it's traveling up into the beaker. Sometimes it's called hot ice because it looks like it's freezing, but it's actually getting warm. And so there, you make all sorts of patterns. In theory, we could, yes. To make these solutions, you have to heat them up, and then you have to wait like half an hour to an hour for them to cool down. There they spell the word ice. Very clever. See, I do not want to play the next one. So, fun with supersaturated solutions. So, the solubility rules that we learned about earlier give us qualitative descriptions. Some ionic compounds, like calcium carbonate, are insoluble because the attraction between the ions is greater than the solvent-solute attraction. But many molecular solids are also soluble in water. And this has a lot to do with the polarity of the molecules. Things like table sugar, sucrose, are polar, and they're very soluble in water. You can dissolve quite a bit of sugar in water, right? Nonpolar solids like lard and vegetable shortening are generally insoluble in water because the attractions that they have between themselves are very different from the attractions between the water molecules. Another analogy I have for this is people speaking different languages. So all of my ancestors came from Sweden. All of my husband's ancestors came from Japan. So I'm going to use the Japanese and the Swedes and hopefully not offend anyone. We'll see. So you get a room full of Japanese people and Swedish people. And the Swedes speak Swedish and the Japanese speak Japanese. Are they going to mix and mingle thoroughly? No. There will be little clusters of Japanese people speaking Japanese. And there'll be little clusters of Swedish people speaking Swedish. They're not going to mix because they don't speak the same language. Now, if they all know English, which they most likely do in today's world, they will mingle because they can communicate with each other. So a nonpolar substance and a polar substance can't talk to each other. There's no attraction, or there's very little attraction between them, and so they're not going to mix. Does that make sense? When ionic compounds dissolve in water, they separate into ions. And so you have individual cations and individual anions in solution. This is called an electrolyte solution. It contains dissolved ions. It's called an electrolyte because it will conduct electricity. You may have heard of electrolytes in terms of rigorous sports and electrolyte replacement solutions. Our bodies need a certain amount of dissolved ionic substances so that we can function. And if you have a situation where you're losing too much fluids, like sweating excessively, and you don't replace those electrolytes, you can get into some trouble. And so that word is used in a very similar way to the way we use it in chemistry. A non-electrolyte solution does not contain any dissolved ions. There's no dissolved charged particles. There's only molecules, neutral particles. An example of this is sugar. Sugar dissolves in water, very much like sodium chloride table salt dissolves in water. But what it forms here are individual molecules and not ions. This solution cannot conduct electricity because there's nothing to carry the current. In chapter 14, we're going to talk about this more, and I'm actually going to do a demo for you, and we'll actually see this happen. The solubility of a substance depends on the temperature. Usually solids are more soluble at higher temperatures and less soluble at lower temperatures. You've maybe observed this if you've ever tried to put sugar in a glass of iced tea that already has the ice in it. It's hard to get the sugar to dissolve, right, when the tea is cold. With hot tea, the sugar dissolves very quickly. Sugar is more soluble at higher temperatures. This graph shows the solubility as grams of solute per 100 grams of water for several different ionic compounds as a function of temperature. We see that some of them, like sodium nitrate, have an extreme temperature dependence. At 50, looks like about 55 degrees, you can have an equal amount of potassium nitrate, 100 grams of it dissolved in 100 grams of water. That would be a saturated solution. So each of these lines represents a saturated solution. If you go down to room temperature, you can only dissolve about 35 grams of potassium nitrate in 100 grams of water. This is how the sodium acetate supersaturated solution comes about. You heat the water to a high temperature where the solubility is greater, and you form a saturated solution at that high temperature. Then you cool it without disturbing it, and like Wile E. Coyote, who doesn't realize that he's walked off the cliff, it just sits there thinking it's fine. And then you give it a little poke, and it goes, oh, wait a minute, I can't have all this dissolved, and it all precipitates out. Things like sodium chloride. Sodium chloride's line here is almost horizontal. It has a very minimal temperature dependence for its solubility. So dissolving salt in a pot of boiling water or a pot of cold water is not going to cause a lot of difference. But most of these, we see that they increase. Some of them are linear, like KCl, NaCl, lead nitrate. Some of them curve. One way to purify a solid is through a process called recrystallization. And this utilizes the temperature dependence of the solubility. So you form a saturated solution at an elevated temperature. So you heat it up and you get as much as you can to dissolve. And then you let it cool slowly. This is normal behavior. Sodium acetate won't do this. Sodium acetate is weird. Very fun, but weird. Most things, as the solution cools and the solubility decreases, the solid will slowly precipitate as it cools. Sodium acetate doesn't do this. It forms a supersaturated solution, then it precipitates out very quickly. When it precipitates slowly, the crystals form slowly, and they tend to reject impurities, resulting in a pure solid. And so you can make your solid more pure by recrystallizing it. Recrystallization is how rock candy is made. They take regular table sugar and make a saturated solution at an elevated temperature. I tried this once when I was much, much younger, And I think my mistake was, because I never got anything out of it, I just had wet, sticky string. I think my error was that I didn't make a saturated solution at an elevated temperature. You heat the water, and you have to put in a lot of sugar. And you get a saturated solution at a high temperature, and you put a string in it, and then you let it cool. And as it cools, sugar crystals will grow on the string. The string gives them a place to form. And the crystals that you'll get here are much larger, and some of them can be strikingly beautiful because as they cool and form slowly, they form a more pure structure. So as it cools, you get the crystals growing on the string. That's something you could try at home if you'd like.